So we are talking about Carnot cycle, and the point here is to prove that entropy is a state function for any gas. And in order to do that, we had a three-step program. The first step was to prove it for a Carnot cycle for a perfect gas. Then the idea is to prove it for a Carnot cycle for any gas. And finally, the idea is to prove it for any cycle for any gas. So we started with Carnot cycle for any gas. We didn't finish it, and I want to do that in full because it's related to the type of things we have been doing. So let's go through it in full. So, and the Carnot cycle shows up a lot. It's worth remembering what it is. So we have an isotherm, we have an adiabat, we have other isotherm, we have other adiabat. So A, B, C, D. This is process 1, which goes like this, process 2, which goes like this, process 3, which goes like this, process 4, which goes like this. This one is isotherm. This one is isotherm at some temperature. The top one is at a temperature T hot, and the bottom one is at a temperature T cold, while these two are adiabats. So what we want to show in this one is that delta S1 plus delta S2 plus delta S3 plus delta S4 equal to 0. That along this closed cycle, this very, very specific, and all processes are taking place reversibly. So this is perfect gas, reversible changes, and Carnot cycle, very specific cycle of a alternating isotherm and adiabat. So it's taking heat from a hot reservoir at TH and giving that heat out to a cold sink at TC. That's what's going on here. And in the process, you're doing work through this, through all of this, through the cycle, you're able to get some work out. And that's what we want to look at carefully. But before doing that, right now we are not interested in work, we are just looking at the entropy. So the Carnot cycle will matter in the work will matter in the next step when we actually think about Carnot cycle for any gas. For now, it's Carnot cycle for perfect gas. So in this one, delta S2 and delta S4 are 0. Why? Because it's an adiabatic change happening reversibly. Both of those statements have to be true. That's why delta S2 and delta S4 are 0. We now need to think about delta S1 and delta S3. Delta S1, we wrote down, is going to be the heat that you take in, QH, divided by temperature TH. There is no integral here because this is an isothermal process. And once again, I want to drive home that just because it's an isothermal process doesn't mean heat is 0. There is heat being taken in. Delta S3 will actually be negative because heat is being given out, but we account for that in the QC term. So QC is going to be negative. So this is going to be TC. So what we want to show, delta S net is equal to QH by TH plus QC by TC. So how do we do this? First, we have to figure out QH. How do we figure out QH? So step 1, let's look at it carefully. QH is the heat taken in by the system during step 1. How to calculate it? This is what I meant by the final exam has to be cumulative because we always start with the first law of thermodynamics. So we say du is equal to delta Q plus delta W. We don't know anything else. But we do two things. We do know two things now. It's an isothermal process and it's a perfect gas. Isothermal process, perfect gas means du is equal to 0. It won't be true for general gas. It's true for perfect gas. So delta Q plus delta W. Therefore, delta Q is equal to minus delta W is equal to PdV. And we can calculate our QH as integral of PdV P is equal to nRT by V. So nRT, it's an isothermal process, so temperature comes out outside. dV by V as we go from VA to VB. So this is nRTH ln VB by VA. By an exactly similar argument, QC is equal to nRTC. Here we went from VA to VB in QC, and in Q cold. The C can be confusing. The C is for cold and also the point C here. Sorry about that overloaded nomenclature. So QC starts from C and goes to D. So B will become D ln VD by VA. Therefore, QH by TH plus QC by TC is equal to NR ln VB by VA plus NR ln VD by VC is equal to NR ln VB VD by VA VC. By the way, in the fourth and fifth homeworks and some of this next homeworks, I will also try to give in some bonus problems, which will be harder, but they will serve two purposes. If clearly last homework was too easy, I mean, 60 of you scored close to 100. So I got to make the homeworks a bit harder without making everyone suffer. So I will be giving bonus problems. You can solve them. If you solve them, you get 120 on 100. And that can help you increase your make up for the things that you have lost in the past. But if you don't do it, you still get 100 on 100, and that's if you solve everything. So we will have a couple of bonus problems in some of the homeworks. So we want to show that this thing, NR, ln, VB, VD, should QC be ln D? Oh, it is. Oh, sorry. Yeah, sorry about that. It is VD by VC, correct. So yeah, I corrected it here. So this is, and we want to show that this thing is equal to 0. How do we do that? So for that, we have to figure out a connection between VB, VD, VA, and VC. So we got to this term by looking at the two isotherms. Where did the TH and TC go? Oh no, they got divided. I divided QH by TH, and I divided QC by TC. That's where they went. I didn't eat them. So now we have to think about the ratio between VB, VD, VA, and VC. So let's look at the adiabats. Now let's focus on this adiabat BC. So for a perfect gas adiabatic process, what can we say? We can say du is equal to delta W, because dq is equal to 0 now. So du is equal to minus pdv. We can, however, also say that du is equal to cv dt for a perfect gas. So cv dt is equal to minus pdv. Here I want to make a comment about one of the homework, about the exam problems. In the exam, we had one problem where the equation of state was given by something of this form. Remember? I mean, you all just did it. And many of you had the question here, can we assume ideal gas? Can we assume ideal gas? And I just kept saying, make the assumptions and go ahead. So this is an interesting one. On one hand, it is not an ideal gas, right? Because the particles have a finite size. On the other hand, if you don't use this relation, I don't think you will make much progress in this problem. So why is it okay to use this relation that du is equal to cv dt during adiabatic change for such an equation of state? How can we justify that? Any ideas? You all took the midterm, so you have thought long and hard about it.
Is it because, well, I guess I don't know if B is defined as a constant in this
B is
sentence.
constant. Let's make your life easy. B is constant.
If B is a constant then and V is a variable for the volume, then you're just modifying that volume term by a constant. And if volume is variable in the ideal gas law, then it's just a variable minus a constant, which you could assume is similar to a variable and just substitute it out.
Yes.
like substitute as like V bar.
Yeah, you're in the right direction, but the point I really want to make here is that as compared to Van der Rohe's gas, it is missing the second term, right? It is this second term that leads to the internal pressure. And I'm going to be lenient here. I don't. If you have just assumed ideal gas and not justified why you did that. I mean, if you have just used this equation and not went through this argument, I will not be deducting points. But I want to mention that there are two ways of looking at it. First is to actually go and calculate partial U by partial V at constant T, the internal pressure, which we can do if we knew the Maxwell relations. We haven't done that. So there is a very mathematical way of showing that this will be true. But even without math, you have to recognize that all this is doing is to take the particles and make them of a finite size. So they cannot sit on top of each other. They are basically like an ideal gas because when they are away from each other, they don't experience anything. So the internal pressure is still zero, and that's why the second term vanishes. So there is a physical way of looking at it, and you won't be deducted points if you didn't do that. I didn't expect that. If you did, that's wonderful. And you can do it completely mathematically by going through the Maxwell relation route, which we'll be doing in a couple of lectures. Again, not expected. If you just use this relation and said that we assume this to be true here, that's totally fine. So we have this. Let's proceed from here. And now we can say CV dt is equal to, yeah. So again, if you had this other term hanging in this equation, then you could not have done that. If anything had this was showing up on the right side, then this problem would be very difficult. It's still solvable, but the answer won't be the same. So we have CV dt is equal to minus NR, PV is equal to nRT, right? So PV is equal to nRT by V dV. So CV dt by T is equal to minus NR dV by V. We integrate this. What do we get? We get Vt to the power k is equal to constant. And we have seen this in the past for an adiabatic process. I really don't care for the value of k here. What is the value of the constant? I'm just going to leave it as it is. So Vt to the power k is equal to constant for perfect gas adiabatic reversible change. I'm going to delete this from the notes. If you have watching the video, you know what it was. Otherwise, it's just going to create distractions during the course of the notes. So what does this mean for us? Vt to the power k is equal to constant along an adiabatic process. So if we look at we have two adiabatic processes. We have BC and AD. So along BC, it means that VB T hot. What is the temperature at B? The temperature at B is TH, right? This is at TH and this is at TC. So VB TH to the power K is equal to VC TC. VC TC to the power K. And similarly here for AD, VA TH to the power K is equal to VD TC to the power K. So we take a ratio of these two things. What do we get? We get VD by VA is equal to TH by TC to the power K. And similarly over here, VC by VB is equal to TH by TC to the power K. Therefore, VD by VA is equal to, therefore, VD by VA is equal to VC by VB, or VB VD by VA VC is equal to 1. Therefore, log of V, what did I write here? Sorry. VD VB. Therefore, log of VD, VB by VA, VC is equal to 0. VB, VD, and that's what we had over here. This is the same log. So this thing is therefore equal to 0. So we just showed that QH by TH plus QC by TC for a Carnot cycle for a perfect gas is 0. And this QH by TH plus QC by TC is our delta S net. Therefore, we just showed for Carnot perfect gas is equal to 0. So that's the first part. Now we have to K is equal to CV by NR, yeah, but I don't know. I don't care for this problem. It's some constant. But if you look from here, that's what it is, I think. But we didn't use it, so I just ignored it. But you're right. So we just showed delta S Carnot perfect gas is equal to 0. Now we have to go to our step 2 of the 3-step program, which is quite interesting, I think, which is to show Carnot cycle for any gas has delta S 0. Before we go into this, I'll just leave this page open if you want to look at it. It's a bunch of algebra, but it's communicating something quite physical, which is kind of the joy of physical chemistry. If you look at it, if you asked your mom or dad or someone else who is not doing any physics or chemistry, that what do you think this is? Is this chemistry or physics or math? Most likely they would say it's math, right? It's some algebra class or calculus class, but it's physical chemistry. And that's where math is really the language which allows us to draw profound conclusions about nature of things around us. So we have step 2 that we need to prove now, that Carnot cycle for any gas has delta S is equal to 0. We just showed it for a perfect gas. Now we have to do it for any gas. In order to do this, we introduce the notion of thermodynamic efficiency. We have mentioned this in passing in the past. Now let's look at it a bit more carefully. Any questions so far about any of this? If any of this not clear, there is no problem in stopping and asking me. And just to be clear, if you ask me a question, I'm not judging you. On the other hand, I'm giving you participation points for asking the questions. I can't go beyond 10, but if you ask me questions, I will happily just bump you up to 10. So please ask me questions. I love when you ask me questions. So, okay, why was DH equal to 0? Oh, very good. Where was DH equal to 0? Where did you see DH is equal to 0? Step 1. Over DH, it's not DH, it's DU. DU is equal to 0 because, good question. So DU is equal to CV dt plus pi t dV, right? Isothermal process, therefore dt is 0. And perfect gas, therefore pi t is 0. No, it's not a bad question. It's sometimes things get confused. And between U and H and everything, I mean, 10 years from now, you will be like, yeah, I once used to know the difference between enthalpy and internal energy. Trust me, a lot of people just forget these things. These are abstract. So these are quite abstract. So introduce the notion of thermodynamic efficiency. How do we do that? So the idea being that we have a hot source. From this, we are extracting some heat QH. We are using this heat to run a motor or run an engine and get some work out W. And first law of thermodynamics tells us that in order for such a process to happen, you must be wasting some heat into a cold sink. QC has to be there, otherwise it will be violated. So we can define the efficiency here as the work performed, how much work did you get divided by heat absorbed from source. And just in order to avoid complications with sign, we will put in modulus. We are just going to look at the absolute value. And this hot source could be some source of energy that you are burning, like burning glycogen versus burning fat in the human body. They have their own different efficiencies. In fact, those of you who like adventure stories, the first people who went to the South Pole, I think it was Shackleton or someone, he has a wonderful book about it. The only thing they could do was to eat up to 20,000 calories of butter worth every day, and they still lost a lot of weight in order to stay warm and hot and everything. It's an amazing story, but basically it's a story of they had only low efficiency food sources left, and that's what they had to consume. Anyway, I got distracted. So how do we write this down here? This is modulus of, if anyone wants the book, I can send you the reference. W divided by modulus of QH, right? So we have had this discussion on Slack. I don't know who was talking about this, is why doesn't QC show here? QC doesn't show here because if all the things were positive, for example, then W is equal to QH minus QC, right? Let's use modulus to keep things significant, to keep things simple. W is equal to modulus of QH minus QC. So as there is a constraint between all three. So you don't need all three to define the efficiency. Two of them are sufficient. So what does this mean? Using this relation, we can write it in terms of QC by QH, 1 minus QC by QH. Now we just showed something for, and this is where the parallels from the Carnot cycle that we drew come in. This hot source could be the isotherm. So we just looked at Carnot cycle, and this hot source could be this part, the TH part, and this cold sink could be the TC part in the bottom, right? So that's what we are looking at. So we just showed, for perfect gas, Carnot, that modulus of QC by QH is equal to TC by TH. And this in turn implied, that delta S Carnot perfect, I'm just using Carnot and perfect in superscript and subscript, is equal to 0. So if we could show that all, and again, we are only talking about reversible changes. Even this thing that we are talking about is a reversible change that is going on. That's a PV diagram in the bottom left, just to show the one we have been drawing in the past for the Carnot. I just wanted to draw a parallel between this engine construction with a source and a sink and how it corresponds to the PV diagram that we drew. Here, we did not care about the two adiabatic parts, but they are going on in parallel. So if we could show that all reversible engines have the same TD efficiency, thermodynamic means, TD means thermodynamic, okay? Just a shortcut, same thermodynamic efficiency, then we have shown delta S Carnot, any gas is equal to 0. This is a subtle point. This is almost like a logical argument. I'm telling you here is that if we could show that all reversible engines have the same thermodynamic efficiency, then that implies that any gas for a Carnot cycle has the same thermodynamic efficiency, has delta S equal to 0. Why is that true? What was the name of the book? I will tell you after the class. It's something about a really, really type 3 journey, something of that sort, by Shackleton. No, type 3, type 2 was not invented. So, where was I? Yeah. Why is this true? Because we know that delta S Carnot for perfect is equal to 0. And we are trying to show that all gases must have the same thermodynamic efficiency, whether they are perfect or imperfect, whether they are real or not, they should have the same thermodynamic efficiency. If we could show that, then since we have already shown for one of them that the efficiency is 0, and that delta S is 0, delta S net along the Carnot cycle is 0. So if we could show this, that all of them have the same efficiency, then we are done, because we have shown that for one of them, this means delta one of them, it is true. So how do we do that? We do it through a mathematical argument, which is called proof by contradiction. So we will be doing this by what is called a proof by contradiction. The most famous example for proof by contradiction is the proof that there exist infinitely many prime numbers. The best way to prove that is to say that, let's say if you have finitely many prime numbers and you reach a contradiction, hence your underlying proof must have been wrong. How do we do this over here? We say, well, let's suppose that it is possible. Suppose it is possible to have two engines. So this over here was an engine, right? This whole contraption was an engine out of which we were getting some work. So let's say it's possible to have two engines with different efficiencies running Oh, I just remembered something I wanted to tell you. Let me check and then tell you. Yes, you remember how we were talking about how people who do thermodynamics and especially statistical mechanics die young? So Carnot also died at the age of 36. So by my age, he was a year dead. Just important trivia for the day. So suppose it is possible to have two engines. That's not the number two. That's the with different efficiencies running reversibly between the same hot source and same cold sink. This is our statement, and we want to show that this will lead to a contradiction. So let's call this engine A and engine B, and we claim that it's possible to construct two such engines that the efficiency of engine A is more than the efficiency of engine B. And what I'm going to show next, that this leads to a violation of the second law of thermodynamics. Hence, this is not possible. Hence, eta A must be equal to eta B. You cannot construct such two engines. And what we are going to show has a very you will see, but it's not really an abstract proof. You will see how it's kind of a common sense proof. It looks abstract, but it is quite common sense. So let's see how we do this. So we have our hot source and we have our cold sink. So hot source and cold sink. And some heat is being taken out from it, which is being used to do some work. This heat is QH, and some heat is being given out to the cold sink, that is QC. So efficiency A will be given by 1 minus QCA by Q hot A. I, I want you to look back at this formula, which we just wrote, and make sure that it makes sense. What we wrote regarding A. How did we define efficiency? Efficiency is work that you get out of the system divided by the heat that you took out of the hot source, which is the same as 1 minus heat that you dump into the cold sink divided by the heat that you get out from the hot source. So, and now we have just put in A because this number is going to be different for engine A than for engine B. So we have put in QCA and QHA. So, and for eta B, it is going to be 1 minus QCB by QHB. And we have, our starting point is that A is more efficient. So eta A is more than eta B. So QCA, so we have the top thing is higher, is larger than the bottom thing. So without loss of generality, we make a further assumption here, which does not really affect our proof. We keep the two cold sinks at the same temperature. Otherwise, the system has too many free parameters. So we say QCA is equal to QCB. Okay, so it is the same cold sink into which we are dumping heat. If we didn't want to do this, we could have kept the hot source at the same temperature, but one of them has to be kept at the same temperature. It does not really affect our argument. So let's say the cold sink is at the same temperature. So what does this mean? This means that eta A more than eta B implies minus QCA by QHA more than minus QCB by QHB. But now we are saying that the numerators are the same. QCA is the same as QCB. What does this mean? This means that therefore 1 over this thing can come to the left side and the minus sign can be gotten rid of. 1 over QHB is more than 1 over QHA, or QHA is more than QHB. In other words, if you are going to keep the temperature of the cold sink same, it must mean that let me write it down. In other words, what we have just shown is that efficiency A more than efficiency B and same cold sink temperature, together these two things mean that the hot source for A is hotter than for B. You can see why, because if they had the same temperature, then WA and WB would also become same, right? And WA is really, and why is this true? Because WA is QHA minus QCA, right? And WB is Q hot B minus QC, Q cold B. And we are saying these two are the same, and while this one is larger, divided by QHA, so it's just simple algebra from which we get this. So this means the hot source temperature for A is more than the hot source temperature for B. So that's interesting. Why is it interesting? Why is it interesting? Because now we can do one thing. We have to do one more experiment, which is, what about if we operate engine B in reverse direction? It's a reversible process. Everything should be possible. There is nothing banned about operating it in the reverse direction. So what we are saying here is that we have an engine A and an engine B. Let's just draw both of them running side by side. This has a hot source at THA. This has a hot source at THB. This has a cold source at TC. Cold source temperature is the same. And this one also has a cold source at TC. This one is giving some work out. It is taking some heat QHA, sinking some heat QCA. And this one, if operated in the right direction, would have done the same thing. It would have taken some heat QCA, QHB, and given out some heat QCB, but we are not doing that. So what we are going to do now is to do it reversibly. We are going to say, what if we do work on this system and take heat out of the cold sink and give it to the hot source? So we are going to take heat QC one moment. Yeah, so we are going to take the heat QC, and we don't need the subscript, the superscript A, because we have set those to be equal, right? So we are taking heat QC out of the cold sink and putting heat QHB out on this. So we know that as per, does this imply WA more than WB? Yeah, that is the whole idea. Thanks, Noel, that's a great question. Exactly, so as Noel said, this construction that we wrote above here implies WA, and let's just stick with modulus, or we can actually skip the modulus. The work being done by engine A is more than the work that you need to drive engine B. So this is WA, and you need to do some work on WB. And the most interesting thing is that this WB can now be extracted out of this WA. It can be used out of the work that you're getting out of the first engine. So this picture can be collapsed into one picture, which I will do on the next page. And I know this is abstract, so please go through my notes. Atkins goes over this in great detail. Please read that the Atkins part also. This part confuses students always. But once you read it a couple of times, it's not that confusing. So since WA is more than WB, the work to run engine B can come from output of engine A. That is the key idea here. So it will almost appear, so together it will appear as if you have a hot source. It will basically be two hot sources and one cold source. And since we are not really interested in the temperature of the hot source, because I wrote down THA and THB here, but we are not really using the temperature in any way. So what I'm going to do is to just think about one big hot source, that is the environment from which heat is being drawn. So a better way to think about it is to not distinguish the temperatures. Let's just call it TH and TC, because we are not even using the temperatures. So this is a hot source and this is a cold sink. The engine A ran over here. It took some heat QHA. It sank some heat QC. This same heat that it sank into the sink was transferred. The same amount of heat was transferred by the other engine. This also takes QC. It's not the same heat, but the same amount of heat. And this is engine A, and this is engine B. And then it takes this and gives back heat QHB to the hot source. And what is the net effect? The net effect, as Noel pointed out, is it was doing WA work, but you are using only WB over here. So the net effect is that this system will still be able to do WA minus WB work overall, because not all of the work is accounted for. So if we further collapse this picture, how will it look like? It will look like we have a hot source and we have a cold sink. And together these two engines, now we can call it AB engine, are allowing us to get work WA minus WB while giving heat QHA minus, giving net heat QHB minus QHA to the hot source. And this is zero, doing nothing from the cold sink, because the left one gave zero to the cold sink and the right one took zero from the cold sink. And we just saw that modulus of QHA minus is more than the modulus of QHB, right? This is something we showed over here. Modulus of QHA is more than modulus of QHB. So this means that QHB is actually negative. So this thing would be negative. So what it's actually going to look, so this is negative. In other words, we can draw it one final one. It's going to look as, let me draw lines here before we all get confused. This is going to look as, you have a hot source, an engine AB, and a cold sink is just sitting there, nothing is happening. This engine is taking work Q hot A minus Q hot B, which we showed is positive here. And you are able to get work WA minus WB out of this. This is not cool, right? We know this violates something. Does anyone remember what does this violate? Anyone wants to help me? Or I'm stuck. Huh? Kelvin or Clausius? It is Kelvin. You're right. Yeah, Kelvin statement. So this makes Kelvin very unhappy. Kelvin sad. In other words, this violates second law of thermodynamics. Therefore, this is not possible. How did we reach this conclusion? We reached this conclusion because we said that it is possible to construct two engines Wait, why was I getting so worried about TH and TC being different? I already stated the whole thing was that we have two engines working between the same hot source and same cold sink. I already said that. Why was I worrying about it? With different efficiencies. If things had different efficiency, you could run one of them in the reverse direction, and you would violate second law of thermodynamics. This proves that all reversible engines have same eta, and we know one specific reversible engine, which is Carnot cycle for a perfect gas, we know the eta. Therefore, all reversible engines have the same efficiency, which is same as all reversible engines have same efficiency for Carnot cycle. Before next time I get butchered on a homework problem. Sometimes I say things and don't write it. That can create problems if you're just looking at notes. All reversible engines have same efficiency for Carnot cycle. Equal to that for a perfect gas, because that is just one such reversible engine, equal to, what is this efficiency? This efficiency is going to be 1, and we know the efficiency is defined by 1 minus QC by QH, and we just showed that for a perfect cycle gas, this is equal to 1 minus TC by TH. Therefore, delta S net equal, let's write down the notation we had before, delta S Carnot any gas. So delta S Carnot any gas is equal to delta S Carnot perfect gas equal to 0. So we have just shown that a Carnot cycle for any gas will have efficiency 0. Now next time we will get to our third step, where we will show that any cycle for any gas can be decomposed into a sum of tiny little Carnot cycles. You can think of it as a mesh made up of lots of tiny little Carnot cycles. And then we will finally prove our final statement that delta S Carnot any cycle for any gas equal to 0. And that will prove our claim that entropy is a state function for any gas. So this is something we are going to next class if you want to read about it. The other thing we are going to do after this is to start with Clausius inequality, which will go back to this notion of what happens to entropy for reversible change, and that will introduce some very useful concepts. So we are basically about to get done with the core construction of thermo, which is these concepts that we introduce. In a few lectures, we will be talking about practical things, which is phase diagrams, chemical equilibrium, a bit of electrochemistry, chemical kinetics. But to do all this, we have to work through this nomenclature and important concepts, which we are almost there. So these are the two things you can read up on for this week. And no office hours today. I will be having office hours next week. Also no office hours for Connor. We have to grade your midterms, and no homework also this week. So you can recover from the midterm. And if you haven't taken the quiz, not the quiz, sorry, the poll, don't get scared about quiz, for the midterm as to how, just an overall sense of how it felt. The link is on Slack. I will also send it to the email. So see you all day after tomorrow.